Microporous crystalline materials such as zeolites and metal organic frameworks have potential applications for use as thin layers in membrane separations. Such microporous membrane materials have a potential for separating a wide variety of mixtures. To give just 5 examples of microporous membrane materials, let us look at DDR, that consists of cages of 278 cubic angstrom separated by 8 ring windows whose aperture is about 3.65 angstrom. ZIF 8 has cages of 1,168 cubic angstrom, and each cage is separated from adjacent cages by flexible 3.3 angstrom size windows. This dimension 3.3 is from the crystallographic information, and we will see later that in practice there is a high degree of flexibility, and guest molecules significantly larger than 3.3 can cross the window regions. Another type of microporous material is X zeolite, Y zeolite. Both have the Faugesite or Fau topology. It consists of cages of 786 angstrom separated by 12 ring windows whose aperture is 7.2 angstrom. We could have one-dimensional hexagonal channels of MOF 74, where M could be magnesium, iron, cobalt, nickel, manganese. Or we could have a set of intersecting channels and use MFI zeolite. MFI stands for mobile 5, and the channel dimensions is 5.5 angstrom, and this is a straight channel and it intersects the zigzag channel. These are the intersection sites. There are 4 intersection sites per unit cell of MFI zeolite. A wide variety of channel dimensions, window dimensions, cage dimensions are possible. And in this presentation, we focus on the important characteristics that determine the performance of a membrane, and that is the membrane permeance and the membrane selectivity. Ideally, we would like to have a combination of high permeance concomitant with high selectivity. However, normally the higher the selectivity, the lower the permeance, and there is usually a trade-off, and we will examine the various factors that determine the permeance and the factors that determine the selectivity of a membrane. One of the important things we would like to stress is that membranes in this category, consisting of narrow windows, have completely different characteristics than membranes that are constructed from materials that have larger channel dimensions or larger window dimensions. Mixture separations using MOFs, ZIFs, or zeolites can be carried out in fixed bed adsorbers using the pressure swing adsorption technology, or in membrane constructs in which the microporous material forms a thin layer, typically less than about 50 micrometers in thickness. There are fundamental differences between the PSA technologies and membrane technologies for mixture separations. If we look at PSA technologies, they are operated in a transient manner using adsorption and desorption cycles. The mixture separations are commonly based on mixture adsorption equilibrium. Usually, intracrystalline diffusion limitations leads to distended breakthroughs, and the productivity of the desired product is lowered. We generally try to avoid diffusion limitations and choose the material, microporous material, in an appropriate manner, and also by adjusting the crystallite size in the packed bed. In exceptional cases, diffusional effects are used to enhance separations or reverse the adsorption hierarchy. For example, the separation of nitrogen from natural gas consisting of methane. In all known materials, methane is preferentially adsorbed, and we would like, in practice, the purified methane to be rejected into the gas phase and nitrogen to be preferentially taken up by the microporous material. The only way to do that is to rely on kinetic separations, in which the pencil-like nitrogen molecule is able to diffuse inside the pores about a factor 20 to perhaps even 100 or 200 faster than methane. Another example is the separation of nitrogen and oxygen. In most materials, nitrogen is most strongly adsorbed due to its significantly higher quadrupole moment. And if we wish to prepare or produce purified nitrogen, one alternative is to use kinetic selectivity, and materials such as LTA4A zeolites, in which oxygen diffuses faster because of its smaller cross-sectional dimension. But generally speaking, PSA technologies are adsorption driven, and diffusional effects are commonly undesirable. Turning to membranes, the situation is quite different. Membrane separations commonly operate under steady state conditions. The permeation selectivity is a product of the diffusion selectivity and adsorption selectivity. We will discuss this extensively in the forthcoming slides. Unlike PSA technologies, intracrystalline diffusion is always important in membrane separations. The separations achieved in membranes are either driven by adsorption or by diffusion. Ideally, diffusion should enhance the adsorption selectivity but this happens in very few cases only, as we shall discuss. And I'll leave with this general remark that the fundamental understanding of mixture permeation across microporous membranes requires insights into both mixture adsorption equilibrium and mixture diffusion. The objective of my presentation is to gain insights into the permeation characteristics of microporous membranes constructed from MOFs, ZIFs, or zeolites. To begin with, let's consider a schematic of a membrane permeation device. We have two components, 1 and 2. N1 and N2 represent the fluxes of components 1 and 2. The upstream compartment has partial pressures P1 and P2 for components 1 and 2. The partial pressures in the downstream compartments are P1 delta and P2 delta, where delta is the membrane thickness. The loadings at the upstream face of the membrane are Q1 and Q2, typically in the units of moles per kilogram. The corresponding loadings at the downstream face of the membranes are Q1 delta and Q2 delta. The component loadings at the upstream face of the membrane can be calculated from the partial pressures P1 and P2 using, say, the ideal adsorbed solution theory, or from experimental data on mixture adsorption, or from molecular simulations. There are two important metrics that govern the separation performance of a membrane device. They are the component permeance, and the component permeance is defined as the flux divided by the driving force. So it is the flux of component I divided by the partial pressure difference between the upstream and the downstream compartments, delta Pi. If we write the expression for the flux as the membrane density times the diffusivity times the difference in the component loadings, Q1 minus Q1 delta, or Q2 minus Q2 delta for component 2, divided by the film thickness. And the driving force is delta Pi, where delta Pi is the partial pressure difference. If the downstream pressures are significantly lower than the upstream partial pressures, then delta Pi may be replaced by just the partial pressures in the upstream compartment. Similarly, if the downstream loadings Q1 delta and Q2 delta are significantly lower than the upstream loadings Q1 and Q2, then delta Q can be replaced by just Q. So we have the permeance as a product of rho times the diffusivity divided by delta times the ratio of the loading to the partial pressure. If we have a unary system, Q divided by P is the Henry constant. For a binary mixture, or say a ternary mixture, the ratio of Q divided by P is to be determined from the ideal adsorbed solution theory. The permeation selectivity can be written as the ratio of the permeance of component 1 and the permeance of component 2. And it's easy to see that this ratio can be rewritten as a product of the adsorption selectivity and the diffusion selectivity. That is, the adsorption selectivity is Q1 divided by Q2 and divided by P1 divided by P2, and this can be calculated using the ideal adsorbed solution theory. And the diffusion selectivity is the ratio of the diffusivities of component 1 with respect to component 2 in the mixture. They are not necessarily the same as the ratio of the unary diffusivities, as we shall discuss. There are effects such as slowing down effects. The slower moving guest molecule slows down the more mobile components in certain cases. There are also what I call traffic junction effects that are important in MFI zeolite membranes. In general, we aim for high permeation selectivity and high permeance. In other words, we aim for to develop a membrane whose performance is dictated by the upper right corner of the Robeson plot. The adsorption selectivity ideally should complement the diffusion selectivity, but this is not a common occurrence. With this background, let us examine the characteristics of different membrane structure. Start our discussions by considering the separation of mixtures of carbon dioxide and methane. Let's take as an example 50-50 CO2 CH4 mixtures at a temperature of 300 Kelvin and a total pressure of 1 megapascals. Using molecular simulations of mixture adsorption and molecular dynamic simulations of mixture diffusion, we determined the diffusion selectivity for CO2 CH4 mixtures and the adsorption selectivity, and for a wide variety of microporous materials consisting of zeolites, ZIFs, sodium X, sodium Y, mordanite, magnesium MOF 74, zinc MOF 74, copper BTC. We determined the adsorption and diffusion characteristics, and they are plotted here, where the diffusion selectivity is plotted against the adsorption selectivity. We note there appears to be two classes of materials. The materials that are indicated in blue here, ZIF8, Chabazite, ERI, DDR zeolite, ITQ29, LTA zeolite, they all have diffusion selectivities larger than unity. All the materials indicated in black have diffusion selectivities lower than unity, and for all the materials the adsorption selectivity is larger than unity because of the quadruple moment of CO2 and the higher degree of polarizability. CO2 is more strongly adsorbed than CH4 in most known materials. Now, to understand the differences between the blue materials here, these consist of cage type structures separated by very narrow windows less than about 4.1 angstrom in size. For example, ZIP8 has an effective window dimension of 3.3 angstrom. Chabazite has an effective diameter of 3.8 angstrom. DDR zeolite has a window dimension of 3.65 angstrom. A difference in the window aperture of half an angstrom is quite important, as we shall see later. The other structures indicated in black, such as magnesium MOF 74, has significantly larger channel dimensions, typically larger than about 5. For example, MFI zeolite has channel dimensions of 5.5 angstroms. MOF 1 has characteristic dimensions of about 9 to 10 angstroms. mil 47 is about 8.5 angstrom channel dimension. The fougescite zeolites have typically the window size is 7.2 angstrom. Magnesium MOF 74 consists of hexagonal channels of 11 angstroms. So let us try and understand why in the materials indicated in black here with characteristic dimensions larger than 5 angstrom, the diffusion selectivity is in favor of methane, whereas in the blue structures, the diffusion selectivity is in favor of CO2 and the adsorption selectivity is also in favor of CO2. We first consider mixtures separations using materials that have characteristic dimensions larger than 5 angstrom, and we start with magnesium of 74. Let's understand the diffusion characteristics of 4 guest molecules: hydrogen, methane, ethane, carbon dioxide in magnesium of 74. I show animations of diffusion of these guest molecules, and these animations are created using molecular dynamic simulations. Let's begin with hydrogen. The molecule is very poorly adsorbed and gets reflected from the framework on striking, and the diffusion characteristics are more or less described by the Knudsen diffusion formula. If we go on to consider methane, you note that there is a higher concentration of methane near the framework walls, because methane has a much stronger adsorption strength than hydrogen and stays longer in the wall regions. And even visually you can see that the mobility of methane is lower than the mobility of hydrogen. Let's move on to ethane. The story is the same. Methane and ethane has a much stronger adsorption strength than methane and stays longer near the wall, and because it's more strongly adsorbed. And you will also note that the mobility of ethane is lower than that of methane. Let's move on to carbon dioxide. And CO2 attaches itself with the unsaturated magnesium atoms located at these vertices, and the binding of CO2 is very strong, and one of the oxygen atoms of CO2 gets bound to the magnesium atoms, and on detachment it undergoes a boomerang-like trajectory if you observe these animations carefully. So the binding strength for adsorption increases here in this direction. The binding strength increases. Hydrogen is lower in binding strength than methane. Methane is lower than ethane. Ethane is lower than carbon dioxide. And even visually, we can see that the mobility appears to decrease with increasing binding strength. Experimental data on the unary permeances of 4 gas molecules, hydrogen, CO2, nitrogen, and methane, have been published for nickel MOF 74, and I plot here the experimental data for the permeances as a function of the kinetic diameter, as is commonly done in the membrane literature. We note that there is a minimum. CO2 has the lowest component permeance, and just to remind ourselves that the component permeance is the flux divided by the driving force, and we can rewrite this as a product of two terms: rho, the density, framework density of nickel MOF 74 times the diffusivity of that component divided by the membrane thickness multiplied by the ratio of the loading at the upstream phase divided by the partial pressure in the upstream compartment. For a unary system, this is the Henry constant. Now, experimental data are available for all these four isotherms for all these four gas molecules. CO2 is the most strongly adsorbed component. Then we have methane, which is very close to the adsorption of nitrogen, and hydrogen is the most poorly adsorbed component. Based on the unary isotherm data, we can determine the Henry constant and back calculate this term, which I call the transport coefficient. You can consider this to be a kind of a diffusivity because the framework density and the membrane thickness are not varying, and we note that the diffusivity of the gas molecules decrease with increasing binding strength. And I plot here the isosteric heat of adsorption that can be determined from the unary isotherm data that is available for each of these components at various temperatures. So CO2 has the strongest binding energy and has the lowest diffusivity. And on the other hand, CO2 has the strongest binding strength. The combination of both the binding constant or the Henry constant times the diffusivity leads to this characteristic. And it is always a source of amazement to me that in the membrane literature, the permeance is plotted against the kinetic diameter. We should not expect the permeances to correlate with the kinetic diameter because the molecular size is not a determinant of the Henry constant. The Henry constant or the binding strength is dictated by polarizability, quadrupole moments, dipole moments, electrostatic interactions, and the rest of it. These are not just functions of the molecular diameter, and certainly the kinetic diameter is not the relevant parameter. The message to emerge from this analysis here so far is sticky guests have low mobilities. In other words, if the component is strongly bound inside frameworks such as nickel MOF 74, remember I'm now considering membrane materials whose characteristic dimensions are larger than 5 angstrom. This is 11 angstrom in size. Sticky guests have low mobilities, and we should not expect the permeances to correlate with the kinetic diameter. Another example of a characteristic such as this is for NH2 mil 125, where again CO2 shows a minimum in its permeance when plotted against the kinetic diameter. Another example to illustrate that sticky guests have low mobility is the data on the unary permeances for hydrogen, CO2, nitrogen, and methane in NH2 mil 125 titanium. The experimental data shows very low permeance for CO2, and this is most likely due to the fact that CO2 is so strongly bound with the NH2 group that it is practically immobilized, leading to hydrogen CO2 selectivities that are extremely high. In this plot, I show the permeation characteristics of cation exchange phagocyte membranes. This is represents phagocyte with no extra framework cations. This is sodium Y with 54 sodium cations per unit cell. This is sodium X with 86 sodium cations per unit cell. With increased degree of ion exchange, we see that the permeation selectivity for CO2 with respect to methane increases by about 1 order of magnitude as we go from no extra framework cations to 86 sodium cations per unit cell. This is a silicon to aluminum ratio 1.23. On the other hand, we note that the permeability of CO2 is decreased by about an order of magnitude with increasing cations. The reason for this is that with increasing degree of cation exchange, the binding strength increases, but the diffusivity of CO2 decreases significantly by about 1 order of magnitude as we go from 0 framework extra framework cations to 86 extra framework cations per unit cell. So increasing binding strength leads to decreasing mobility and decreasing CO2 permeability. So in practice, the degree of ion exchange in cation exchange zeolites can be tuned to optimize the membrane performance. I wish to illustrate another important concept in mixture permeation across microporous membranes, and to do this I consider CO2 hydrogen permeation across an MFI membrane. This is a graph showing experimental data published by Sandstrom, who measured both component permeances in the mixture as well as unary permeances. The unary permeances are shown by the open symbols. The open diamonds are for hydrogen. The open circles are for CO2. The red circles are for CO2 permeance in the mixture, and the yellow diamonds are the hydrogen permeance in the mixture. For the mixture permeation, the experiments were carried out for equimolar hydrogen CO2 mixtures in the upstream compartment. The permeances are plotted against the upstream partial pressures measured in megapascals. It's interesting to note that the hydrogen permeance in the mixture is lower than the unary permeance by about 1.5 to 2 orders of magnitude. The CO2 permeance in the mixture is only slightly lower than the unary permeance of CO2. There are two reasons why the hydrogen permeance in the mixture is lowered by about 2 orders of magnitude. There are two separate reasons. Firstly, the mixture adsorption favors CO2 because CO2 is more strongly adsorbed. And secondly, the tardier or the less mobile CO2 has the effect of slowing down the more mobile hydrogen. And this slowing down effect needs to be understood and quantified in order to understand mixture permeation across MFI membranes. In order to understand how the most strongly adsorbed CO2 molecule reduces the mobility of the poorly adsorbed hydrogen, we have a look at the animations of the motion of CO2 and hydrogen within the intersecting channels of MFI zeolite. These animations are created from MD simulations. Let's have a look. Here we see the CO2 molecules and the gray spheres are the hydrogen molecules. We see that the hydrogen molecules have high mobility, but somewhere along the channels, they encounter a more strongly adsorbed CO2 molecule, and they cannot go past the CO2 molecule. That has the effect of hindering the mobility of hydrogen. Let's have a look again. And if we observe closely, we see that the path that a hydrogen molecule can traverse in its journey is reduced because it will encounter a strongly adsorbed CO2 somewhere along the channel, and that CO2 molecule will prevent hydrogen from proceeding further in its diffusion path. Here I use the analogy with a checkerboard to explain the slowing down effects that hydrogen experiences in mixtures with CO2 within the intersecting channels of MFI zeolite. Here's the checkerboard where each of these squares represents an adsorption site within MFI zeolite. The red circles are CO2 molecules that are strongly adsorbed, and therefore each of these red circles vacates or hops to another adjoining site at a frequency that is much lower than the frequency with which hydrogen, the smaller molecule, jumps from one site to an adjacent site and traverses the intersecting channels of MFI. I draw here a contour that the more mobile hydrogen can occupy, but to go beyond that contour, CO2 has to vacate that adsorption site. So it is akin to a game of musical chairs. For hydrogen to occupy a chair, that chair has to be first vacated by the tardier, more strongly adsorbed CO2. Put another way, the mobility of hydrogen is correlated with the mobility of the tardier partner CO2. And the net result is a slowing down of hydrogen in mixtures containing CO2. The slowing down of the motor cars by the tardier elephants is entirely analogous to the slowing down of hydrogen by the most strongly adsorbed tardier CO2 within the intersecting channels of MFI zeolite. For CO2 CH4 mixture diffusion in MFI zeolite, the mobility of methane is severely reduced due to the more tardy CO2 that has a stronger adsorption strength. We can have a look at the animation to illustrate that. We can see that the CO2 molecule refuses to budge from the intersection sites, and therefore preventing the methane molecules to travel very far along the channels. Let us examine the experimental data for permeation of mixtures of normal butane and isobutane across an MFI membrane. This table here shows the data on both unary permeances and the permeances in binary mixtures. Quite interesting to note that the permeance of NC4 in the mixture is lower than the unary permeance. The permeance of IC4 in the mixture is also lower than the unary permeance. And the permeation selectivity for the mixture is higher than the ideal separation factor for unary permeation. We need to understand what causes the lowering in the component permeances of both NC4 and IC4 in the mixture as compared to the unary permeance. And I shall demonstrate that the reasons are different. For IC4, the reduction in the permeance of IC4 in the mixture as compared to the unary permeance is due to mixture adsorption that favors the normal isomer. And I would like to demonstrate that this preference for NC4 is due to configurational entropy effects. I would also like to show that the reduction in the NC4 permeance from 4.4 to 3.3 in the mixture is due to traffic junction effects due to blocking of some of the intersection sites due to preferential location of the isobutane at the intersection sites. So there are two separate effects: entropy effects for mixture adsorption and traffic junction effects for mixture diffusion. The unary isotherms for normal butane and isobutane in MFI zeolite are plotted here. The red circles are for normal butane, the green squares are for isobutane. We note that the isobutane isotherm shows a strong inflection at a component loading of 4 molecules per unit cell. Per unit cell of MFI zeolite, there are 4 intersection sites, and isobutane prefers to locate at the intersection sites because of legroom considerations. It's configurationally easier for isobutane to locate at the intersection sites. This can be observed if we view the animations. We see isobutane has a rotational degree of freedom at the intersection sites, and we need an extra push in order to have isobutane locate within either the straight channels or the zigzag channels. So isobutane has a configurational penalty because it has preferential locations, sites at the intersection points. Normal butane can locate freely along the zigzag channels or along the straight channels. Here I plot the adsorption selectivity against the total loading of the mixture. At very low loadings, the selectivity is unity, and both on normal butane and isobutane have the same loading. However, as the total loading increases, the adsorption selectivity is increasingly in favor of the normal isomer because the partner molecule, isobutane, is entropically challenged. And the selectivity increases significantly in favor of normal butane as the total loading increases. So the entropy effects explain why the isobutane component permeance in the mixture is lower than the unary permeance as measured experimentally. Isobutane has a significantly lower diffusivity by about 3 to 4 orders of magnitude than normal butane. And since isobutane prefers to locate at the intersection, effectively it blocks the intersection sites. Let's have a look at the animation. We note here the isobutane molecule is preventing the normal butane molecule to cross the intersection points. And the traffic along the channels, straight channels and zigzag channels, is considerably slowed down due to intersection blocking. This is demonstrated from the experimental data that plots the diffusivity of normal butane with increasing loading of isobutane. With increased loading of isobutane, the normal butane diffusivity in the mixture is reduced by about 2 orders of magnitude if there are 2 molecules per unit cell at the intersections. So if 2 intersection sites are blocked, the normal butane diffusivity is reduced by about 2 orders of magnitude. And if all the intersection sites are blocked, then the traffic is brought to a complete standstill. This intersection blocking effect explains why the experimental data shows that the normal butane diffusivity or normal butane permeance in the mixture is lower than the unary permeance of normal butane as observed in the experimental measurements at Dalian. If the intersections are blocked, the entire traffic along this channel and this channel is brought to a complete standstill. Entropy effects also play an important role for permeation of mixtures of normal hexane and 2,2-dimethylbutane across an MFI membrane. Here I show experimental data for the component permeances of NC6 and 2,2-DMB. The filled symbols are for mixture permeation and the open symbols are for unary permeance. We note that the 2,2-DMB permeance in the mixture is reduced by about 2 to 3 orders of magnitude below the value for unary permeance, whereas for NC6 the permeance in the mixture is almost the same as the unary permeance. To understand this strong reduction in the component permeance for 2,2-DMB, we have to understand that the mixture adsorption is dictated by entropy considerations. 2,2-DMB is a branched alkane molecule that prefers to locate at the channel intersections, and there are only 4 channel intersections, and therefore if you look at the unary isotherm for 2,2-DMB, we will note that the unary isotherm is limited to a saturation capacity of 4 molecules per unit cell. Normal hexane can locate along the straight channels, can locate along the zigzag channels, and achieves a total saturation capacity of 8 molecules per unit cell. So in a mixture of 2,2-DMB and NC6, the mixture adsorption is shown by the fill symbols. The red ones are for normal hexane, and the green squares are for 2,2-dimethylbutane, we note that with increasing pressure in the bulk gas mixture, the normal hexane loading increases at the expense of 2,2-dimethylbutane, and 2,2-dimethylbutane is virtually excluded from the pores due to entropy considerations. And the result is that the component permeance for 2,2-dimethylbutane is significantly lower than the unary permeance for 2,2-DMB. In the second part of this presentation, I consider membranes that are constructed of materials that consist of cages separated by windows that are smaller than about 4.1 angstrom. For example, you could have a Shabasite, consists of cages of 316 cubic angstrom, separated by 8-ring windows. This is 3.8 angstrom here and 4.2 angstrom in this direction. This is DDR zeolite, consists of cages of 278 cubic angstrom, separated by 8-ring windows, 3.65 angstrom here and 4.4 angstrom here. A small difference in the window aperture is quite important and has a significant influence on the intra-cage hopping of molecules from one cage to the other. This is LTA zeolite, consists of larger cages, 743 cubic angstrom, separated by windows of 4.1 angstrom here, 4.5. The minimum dimension of the window is important because that dictates the diffusivity. ZIF8 has cages that are 1,168 cubic angstrom in size, and the windows separating two adjacent cages are 3.3 angstrom, but the windows are flexible. Let us try and qualitatively understand the reasons for the high values of the diffusion selectivity of CO2 with respect to methane for cage window structures such as ZIF8, Shabasite, LTA, DDR, etc. In order to do that, let's look at MD animations of the intercage jumping of molecules. We start with Shabasite on the left-hand side. Have a look at this CO2 molecule. It is hovering near the window region and is crossing the window at this site. Note that the CO2 jumps lengthwise across the windows. Lengthwise. If you look at the dimensions of CO2, the cross-sectional dimension is 3.1 angstrom and the length of the molecule is 5.4 angstrom. So the relevant dimension for lengthwise jumping of CO2 is 3.1 angstrom, and that should be compared to the value of 3.7 angstrom for methane. It's also to be noted that the kinetic diameter of CO2 is 3.3 angstrom, but this is irrelevant for cage window structures with narrow windows because of the lengthwise jumps. A kinetic diameter is not to be used. Let's look at the animations for LTA zeolite. Again, we note that the CO2 molecule jumps lengthwise across the windows. This is true for all cage window structures denoted in blue here. Another point to note, and that should be obvious from these animations, is that the gas molecules jump one at a time across the windows, and there are no slowing down effects because of the one at a time jumps. Slowing down effects such as those demonstrated for materials with channel dimension greater than 5 angstrom are not relevant for cage window structures. This makes the analysis of diffusion easier because the unary diffusivities can be identified with the diffusivities of that component in the mixture. But the comparison should be made at the same pore occupancy, as we shall see later. In this graph, I show molecular dynamic simulations of the diffusivity of methane in DDR, Shabasite, LTA zeolite, LTA 5A, and LTA all silica zeolite. We note that as the window dimension, or the minimum aperture of the windows, increases from 3.65 to 4.1, the diffusivity of methane increases by about 2 orders of magnitude, and the CO2 methane diffusion selectivity decreases by about 1.5 orders of magnitude as we go from DDR to LTA zeolite. So the molecular dimensions with respect to the window dimensions are of crucial importance in determining the molecular diffusivity across the windows and the CO2 methane diffusion selectivity. Consider nitrogen methane diffusion inside the cage window structures of DDR zeolite that consists of cages of 278 cubic angstrom separated by windows that have dimensions 3.65 in this direction and 4.4 angstrom in this direction. The relevant dimension is 3.65, the minimum aperture. We note from the MD animations that nitrogen jumps lengthwise across the window from one cage to the adjacent cage, and the relevant dimension for diffusion is 3.3 angstrom. The kinetic diameter of nitrogen is 3.64, but that is irrelevant, and just as in the case of CO2, the relevant dimension for nitrogen is the cross-sectional dimension, and the diffusivity of nitrogen is significantly higher than the diffusivity of methane because of these differences in these dimensions, 3.3 against 3.7. The adsorption favors CH4, the diffusion favors nitrogen, and the permeation selectivity across a DDR membrane is in favor of nitrogen because the diffusion selectivity overrides the adsorption selectivity that favors methane. The description of diffusivities of gas molecules inside cage window structures such as Shabasite, DDR, LTA, ZIF8 are much simpler than the diffusivities for the materials considered in part 1, because for cage window structures, the diffusivities depend only on pore occupancies and not on the partner molecules, because an important factor is that the molecules jump one at a time across the windows, and there are no slowing down effects as shown in materials such as MFI, magnesium MOF 74, Faugisite, MIL 125, etc. So the diffusivities are dependent only on pore occupancy or not on partner molecules. I demonstrate this only for Chabasite. These are the diffusivity of CO2, methane, nitrogen, and hydrogen. And in each case, we compare the unary diffusivities with diffusivities in various binary mixtures and ternary mixtures. For CO2, the diffusivity is uniquely dependent on pore occupancy. The same is true for methane. Whether it's unary methane or methane and CO2 to methane mixture, or CO2 methane and methane nitrogen mixture, or methane and CO2 methane nitrogen mixture, or methane in methane hydrogen mixture, the diffusivity is unique function of pore occupancy. Same is true for nitrogen. Same is also true for hydrogen. Whether it is pure hydrogen or hydrogen in presence of CO2, the diffusivity only depends on the occupancy inside the pores. The occupancy is defined for a binary mixture as the loading divided by the saturation loading of component 1, and you add the occupancy of component 2, which is the loading of component 2 divided by the saturation loading. This makes it easier to model and understand component permeances in mixtures, because the diffusivity in the mixture is the same as the unary diffusivity, provided we make the comparison at the same pore occupancy, and therefore the component permeance in the mixture is only dictated by mixture adsorption, and we can use the unary diffusivity data to describe mixture permeation. Let's examine the data determined in experiments for the permeances of CO2, methane, nitrogen, and hydrogen in SAPO34 membrane that has the same structural topology as Chabasite. Just to remind ourselves, the permeance can be written as the framework density times the diffusivity times the driving force. This is the difference in the loading on the upstream phase minus the loading in the downstream compartment, divided by the difference in the partial pressures. And this is the membrane thickness. We have established in the last slide that the diffusivity of any component in the mixture can be identified with the diffusivity of the pure component, provided the comparison is made at the same pore occupancy. So we don't need to worry about this. This can be estimated from unary diffusivity data that can be determined from unary permeation experiments. But this factor, delta Q divided by delta P, is determined by mixture adsorption equilibrium, and this cannot be identified with the corresponding delta Q divided by delta F value for unary permeation. That means that the component permeances in the mixture are different from the component permeances for pure components, but the differences are purely due to mixture adsorption effects that can be estimated or predicted using the ideal adsorbed solution theory. Let's examine the experimental data in some more detail. The unary permeances of each of the components are shown by the open symbols, circles, open circles are for CO2 unary permeance. In the mixture of CO2 with methane, the permeance is the same as for the unary permeance. This is because CO2 is much more strongly adsorbed than methane, much more strongly adsorbed than nitrogen, much more strongly adsorbed than hydrogen. And therefore, in all the mixtures, the component permeance of CO2 is practically unaffected by the partner species because CO2 is the dominantly adsorbed component. The situation with regard to methane, nitrogen, and hydrogen are different because it depends, their permeances depend on the partner species. For example, here we have the unary permeance of methane shown by the open square symbols, and the red circles are the component permeance of methane in a mixture with CO2. There is a significant reduction in the methane permeance in the mixture compared to the unary permeance because of mixture adsorption equilibrium, but that can be determined from the IAST. If we look at a mixture of nitrogen and methane, the permeance of CH4 in the mixture with nitrogen is shown by the inverted triangles here, and there is hardly any difference because methane is more strongly adsorbed than nitrogen. Therefore, the nitrogen does not offer any competitive adsorption to methane. But the reverse is true for nitrogen permeance. These are the pure component permeance of nitrogen, and this is the component permeance for nitrogen in mixtures with methane. The component permeance for nitrogen in mixtures with methane is lower because of competitive adsorption, and CH4 is more strongly adsorbed, and therefore there is a lowering in the permeance. If we have considered a mixture of nitrogen with CO2, the lowering in the component permeance is still greater, and you can see there's a factor 2 to 3 reduction in the component permeance of nitrogen in mixtures with CO2. And this is for a ternary mixture of nitrogen in a mixture of CO2 and methane. We see a significant reduction. Hydrogen is the least strongly adsorbed molecule, and the component permeances in mixtures with nitrogen as partner, with methane as partner, or with CO2 as partner are all significantly lower than the unary permeance because of competitive adsorption effects. I repeat, the diffusivity of a component in a mixture is identifiable with the unary diffusivities, and the component permeance in cage window structures such as Chabasite, DDR, LTA, ITQ29, ZIF8. The component permeances in mixtures can be estimated by using the unary diffusivities that can be backed out from unary permeation data, along with mixture adsorption equilibrium estimates using the IAST. For strongly adsorbed components such as CO2, the component permeance in the mixture is the same practically as the unary permeance. For more weakly adsorbed components such as methane, nitrogen, and hydrogen, the permeance in the mixture is severely reduced due to partnering up with more strongly adsorbed partner molecules. The message to emerge from this graph is that mixture permeation in cage window structures are more easily predictable than for materials that contain topologies with pore dimensions larger than 5 angstrom, because in these structures such as Chabasite DDR, slowing down effects traffic junction effects are not relevant. We plot the same set of data for the component permeances for CO2, methane, nitrogen, and hydrogen, not as a function of the partial pressure in the upstream compartment, but by the occupancy of that component at the upstream face. I define the occupancy, the fraction on occupancy, as the loading of that component divided by its saturation capacity, plus the loading of the partner species Q2 divided by the saturation capacity of 2. These can be determined from knowledge of the unary isotherms and mixture adsorption equilibrium calculated from, say, the ideal adsorbed solution theory. If the component permeances are plotted against the occupancy at the upstream face, we see that there is a very good correspondence between the component permeance in the mixture with the unary permeance. This is true for CO2. This is true for methane. And we note that the lower permeance in mixtures with hydrogen is because, in mixtures with carbon dioxide, is because CO2 is much more strongly adsorbed, and therefore the occupancy of that component in the upstream phase is high, and the component permeance reduces with increasing occupancy. The same is true for nitrogen. Plotted against the occupancy at the upstream phase, the data for unary permeance and component permeances all lie on a single line. The same is true for hydrogen. This is the unary permeance data, and the component permeances in mixtures with CO2, mixtures with hydrogen, and mixtures with nitrogen, they all lie on a unique line. So the component permeances are strongly dependent on the occupancy in the upstream compartment. In this presentation, I have made a distinction between two classes of materials. Firstly, we have cage window structures in which the window dimensions are less than 4.2 angstrom. In this case, an important parameter that dictates the permeation properties is the minimum dimension of the pore of the window opening. Small differences between the window aperture leads to differences in diffusivities by about 2 orders of magnitude. And this can be exploited to obtain high permeation selectivities. Another point that was emphasized is that pencil-like molecules such as carbon dioxide, nitrogen jump lengthwise across the channels, and it is pointless to talk in concepts of the kinetic diameter. Moving on to the second class of materials, in which we have window or channel dimensions larger than about 5 angstrom. Here again, we have emphasized that the concept of the kinetic diameter to correlate component permeances is irrelevant or not applicable, because the permeance in such structures is dictated by the stickiness or the binding strength of the molecule. Sticky molecules have lower mobility. This influences the permeation selectivity and the diffusion selectivity. There is also a further effect that has been highlighted, and that is due to the correlations between the jumps of molecules. A CO2 molecule that is stickier reduces the mobility of more mobile partners. We've also highlighted for MFI zeolite the concept of intersection blocking. If the intersections are blocked, then the whole traffic can be brought to a standstill. And finally, we have also mentioned the mutual slowing down due to hydrogen bonding between molecules. In this presentation, I have made a distinction between two classes of materials. Firstly, we have cage window structures in which the window dimensions are less than 4.2 angstrom. In this case, an important parameter that dictates the permeation properties is the minimum dimension of the pore of the window opening. Small differences between the window aperture leads to differences in diffusivities by about 2 orders of magnitude. And this can be exploited to obtain high permeation selectivities. Another point that was emphasized is that pencil-like molecules such as carbon dioxide, nitrogen jump lengthwise across the channels, and it is pointless to talk in concepts of the kinetic diameter. Moving on to the second class of materials, in which we have window or channel dimensions larger than about 5 angstrom. Here again, we have emphasized that the concept of the kinetic diameter to correlate component permeances is irrelevant or not applicable, because the permeance in such structures is dictated by the stickiness or the binding strength of the molecule. Sticky molecules have lower mobility. This influences the permeation selectivity and the diffusion selectivity. There is also a further effect that has been highlighted, and that is due to the correlations between the jumps of molecules. A CO2 molecule that is stickier reduces the mobility of more mobile partners. We've also highlighted for MFI zeolite the concept of intersection blocking. If the intersections are blocked, then the whole traffic can be brought to a standstill. And finally, we have also mentioned the mutual slowing down due to hydrogen bonding between molecules. In this presentation, I have made a distinction between two classes of materials. Firstly, we have cage window structures in which the window dimensions are less than 4.2 angstrom. In this case, an important parameter that dictates the permeation properties is the minimum dimension of the pore of the window opening. Small differences between the window aperture leads to differences in diffusivities by about 2 orders of magnitude. And this can be exploited to obtain high permeation selectivities. Another point that was emphasized is that pencil-like molecules such as carbon dioxide, nitrogen jump lengthwise across the channels, and it is pointless to talk in concepts of the kinetic diameter. Moving on to the second class of materials, in which we have window or channel dimensions larger than about 5 angstrom. Here again, we have emphasized that the concept of the kinetic diameter to correlate component permeances is irrelevant or not applicable, because the permeance in such structures is dictated by the stickiness or the binding strength of the molecule. Sticky molecules have lower mobility. This influences the permeation selectivity and the diffusion selectivity. There is also a further effect that has been highlighted, and that is due to the correlations between the jumps of molecules. A CO2 molecule that is stickier reduces the mobility of more mobile partners. We've also highlighted for MFI zeolite the concept of intersection blocking. If the intersections are blocked, then the whole traffic can be brought to a standstill. And finally, we have also mentioned the mutual slowing down due to hydrogen bonding between molecules.